Hello everyone and welcome to lecture 7 on heat exchanger design. In this part of the lecture we will look at the overall heat transfer coefficient without fouling. Okay, so at the end of this lecture 7 you should be able to understand how we can calculate the heat transfer coefficient, overall heat transfer coefficient, and how we can include the effect of fouling for the value of overall heat transfer coefficient. What are the steps to design a heat exchanger design, and also how we can develop temperature profiles in a heat exchanger. And finally we look at the overall design of the heat exchanger. So let's look at overall heat transfer coefficient without fouling. So when as we discussed in the previous lecture, when we were talking about different classifications of heat exchangers, we said that mainly there are two primary problems in heat exchanger design. The first one is when we are looking at the calculation of heat transfer duty for an existing exchanger. Okay, so what it means that we have already an exchanger and we know its area, and we want to know what kind of heat duty this area can give us. Okay, so that is what we call a rating problem. Okay, so we are just rating the heat exchanger if it is going to work for a duty, because you might have changed the conditions of the process or you might have changed the temperature. So as such, the duty is different now of the process, but you have already purchased a heat exchanger for a previous conditions, so you don't want to buy another one. And so you are looking if your existing heat exchanger is going to work in the new situation or not. Okay, and that is what we call the rating of the heat exchanger. And then we have another problem, that what we call the sizing of the heat exchanger, and that is when you are designing a new heat exchanger. Okay, so what you know is that what kind of heat duty, what is the amount of heat load that you have in the process, and you want to calculate that how much area you want for that particular heat transfer. Okay, because when you buy a heat exchanger you have to give them what is the area of heat transfer, and based on that the mechanical engineers, for example, they design a heat exchanger for you or build a heat exchanger for you. Okay, and in most of heat exchanger design, and actually also in any kind of heat transfer around the surface, we are mostly looking at this equation here. Okay, and here we have again Q and A. So these two terms, either one of them is given or you need to calculate. Okay, so if Q is given you need to calculate A, and if A is given you need to calculate Q. Okay, and in order to do these calculations of Q and A, we need to know what is the overall heat transfer coefficient and what is the driving force. Okay, in most of the cases we know the driving force easily because we are the designers, so we know what kind of temperatures we want from the process, and then we look for a suitable value of U. Okay, so this is more or less what is explained, more or less what I explained in the previous slide. So here again, in the first case, you want to calculate Q, okay, and you need to know you have the value of A, for example. Okay, so A is given, you need to calculate Q, and here you have, for example, Q is given and you need to calculate A. Okay, and in both cases, as I said, these are the parameters that you need to evaluate to get to the value of Q and A. Okay, so in the previous lecture, again, as I said, that shell and tube heat exchanger is one of the most common heat exchangers. Almost around 60 to 70% of exchangers in industry are shell and tube heat exchangers because they are very versatile, they are very cheap compared to other exchangers. So most of the industry like to use shell and tube heat exchangers. So when you will become, for example, a professional engineer, you are very likely to come across a shell and tube heat exchanger. Okay, So in terms of design of heat exchanger, we are going to focus mainly on shell and tube heat exchanger, okay? But the concepts can also be used on other type of heat exchangers like plate and frame heat exchanger or compact heat exchanger, okay? So here we are looking at shell and tube heat exchanger. So what is happening, and I hope you remember from the previous lecture when we talk about different classifications. So shell and tube heat exchanger, you have a bundle of tubes. So all these lines, actually the light color lines, they are tubes, okay? So it means that the tubes are fixed in this two headers, and then you have so the liquid that is coming through this header goes through the tube and then pass all the way and then comes out here, and then at the end of you have the sum of all the liquids that are coming from the tubes, and then it goes out, okay? On the other hand, the shell is around the tubes, okay? So the liquid in the shell, that is, for example, it is coming from the top because of the gravity effect, is mostly come from the top, and then you have the outlet at the bottom, and then the liquid of the shell is not in contact with the liquid of the tube, but the liquid of the shell is in contact with the wall of the tube, okay? So if you look at only one, for example, tube, so this is the tube where you have, let's say, hot liquid is coming from here and it's going on this side, and then you have the shell, and let's say this is the shell around it, and for the shell, the cold liquid is going in this part and then coming from this part out, okay? And so if the temperature of the tube fluid is not equal to the shell fluid, okay, then we can say that the heat exchanger can happen. The heat exchange can happen. Okay, so if the two temperatures are equal, obviously the net rate will be 0. Okay. So now let's look at what can be the situation. For example, if we are looking at the heat exchange between, as I said, that the main heat exchange is around the tube. So let's say you have this tube again, and around the tube, this is the shell part. Okay, this is the shell part. So this is the surface of the tube. So if you look at the surface of the tube here, for example, you will see that on the inside of the tube you have, let's say, a hot fluid. Okay, so inside the tube here you have convection as well, because the fluid is moving, so you have convection. And then you reach to the wall, and in some cases, or in most of the cases, you always get some kind of fouling, the scaling kind of thing. And then the heat from this point to this point, you have the conduction heat transfer inside the fouling layer that is on the inner side of the tube. Okay, and then you have the thickness of the tube, okay, the wall of the tube itself, where you have the second convection. Okay, so you have a conduction, sorry, and then you have another layer of the fouling on the outside of the tube. Okay, so that is the shell side now. So here we are in the shell, and here is the tube side. So here again you have the fouling, and then you have the heat transfer in the fouling, and finally you have, let's say, cold fluid here, and then you have convection in the cold fluid. So you have 5 different forms of heat transfer. You have 2 convections and 3 conductions. Okay, because you have convection here, then conduction here, then conduction here, then conduction here, and then here you have the second convection. Okay, so that is what is happening inside the tube. Now if we try to look at how we can calculate the overall resistance, okay, and all these things are happening in series. Okay, as you can see that all these things are connected, and so they are in series. So we can calculate the R total. How we can calculate the R total? To do the calculation of R total, we look at the overall heat transfer coefficient. Okay, so R total gives us the total resistance to heat transfer, and opposite to that we have 1 over U, and U actually is the overall effectiveness of heat transfer. Okay, so it's the opposite of resistance. Okay, so we want to calculate this U. So let's now consider a case where, let's say, you have the tube. So this is the tube here. Again, this is a 3D tube, so you have length h. Okay, so you have length h here, and the inner radius of the tube is Ri, and the outer radius of the tube is R node. So the difference of these two radius gives you the thickness of the tube, okay, or the thickness of the wall. So now if you look at, again, because you don't have any fouling, so you have convection on the outside the tube on the shell side, then you have conduction here in the wall, and then you have, again, you have convection inside the tube. Okay, so you have convection, conduction, and convection again. So if you put these three in series, we can calculate what is the overall resistance. So you can call it, for example, RT or RO, like R overall, and that should be equal to 1 over UA is equal to 1 over AIHI, that is the resistance on the inner side of the tube due to convection. Then you have the resistance due to conduction, and then you have the finally again the convection on the outside of the tube. So the resistance due to convection on the outside of the tube. And here, if you look, we are using, for conduction, we are using log mean log area, and the reason is that because we are in a cylindrical system, so as we are moving along the radius, the surface area keep on changing. Okay, so it is different from a planar wall, because as we are considering, for example, a cylindrical system, so the change in radius cause a change in the surface area. So we have to calculate the log mean surface area. Okay, and you have done this in lecture 2 with Wenny. Okay, so we are kind of comparing the effectiveness or the effective area that is actually in use for the heat transfer. And another thing, how we know that R total is equal to 1 over U. So again, we go back to our main equation, that is Q is equal to UA delta T. Okay, and we also know that Q is equal to delta T over R. So if you compare these two equations, the delta T will cancel out. Okay, and it means that we will have 1 over R is equal to UA. Okay, and then you can write it in a slightly form of R. So let's say you have R that is equal to 1 over UA. Okay, so we can derive this equation here. So now a little bit about the log mean area. Okay, and as I said that the log mean area, you have already looked at it in lecture 2, that is equation 2.13. Okay, so if you don't remember, please go have a look back. And why we are calculating this log area is because we are looking at that if you compare a cylindrical system with, for example, a slab or a planar surface, how the area will change. Okay, and so we can write R conduction in this form here. Okay, and this R conduction is actually based on this AM. Okay, and that AM is given to you by this equation. Now what is interesting here is that if you are in a situation where you have thin walled tubes, it means that the thickness of your wall is negligible. It means that Ri is actually more or less, for example, equal. So you can assume that the thickness is really negligible. It means that R node over minus Ri will be 0, and it means that the conduction resistance is also negligible. Okay, so it means that the value of R conduction will become 0. Okay, and same thing you can observe it here as well. We know that if R's are equal, then the value of this, for example, the ratio of areas will become 1 and log 1 is 0. So again, the area will be negligible. Okay. And it means that if you are in a system where you have thin walled surfaces, we can consider that the R conduction is 0, and as such we can actually cross this equation here. We can just cross this part of the equation, because that will become 0, and we only left with the convection on the inner side of the tube and the convection on the outside of the tube. And we can ignore this conduction because the resistance due to this thin wall of tube is negligible. Okay. And so if you use this formulation, you can calculate what is the overall heat transfer coefficient. So just to simplify it or summarize it, that the total resistance, that is R, is equal to 1 over UA, and this total resistance is equal to 1 over HIAI plus 1 over H node A node. And if we have thin walls, we can write it like this. But if we have, for example, thicker walls, then we have also need to account for the conduction resistance, and then we can use this equation as a whole. So if you need to calculate the value of U, you just need to use this equation and you can calculate what is U for a clean surface. In the next part, we will look at what would be the effect of fouling on this U. If, for example, here we have no fouling, so if we have fouling, how it will change the value of U. Okay, so let's talk about that in the next part. Thank you for your time.